Hello everyone, my name is Natalie Parker. Today I will be discussing the research I conducted over the summer with Dr. Barry Chung. My research uses a computer simulation called ZD Plaskin to observe plasma. Plasma is an ionized gas, used within chemistry for surface modification and supplying large amounts of energy. This project works with a specific kind of plasma known as weakly ionized plasma. It is non-thermal, selectively reactive, and it works as a multi-component system with varying temperatures and molecule sizes. The plasma pipette is a handheld device that uses weakly ionized argon plasma. The project goal was to model a mixture of argon, water, and oxygen plasma by modifying the ratio of water to oxygen density. ZD Plaskin is a Fortran-based software that incorporates a differential equation solver to quickly simulate the plasma in set environments. The software uses Kinetics to predict the behavior of multiple reactions at once based on predetermined rate constants and cross-sections pulled from the IST Lisbon database. In Figure 1, located in the bottom right of my method section, it provides a guide on how the software uses the Maxwell-Boltzmann reactions to predict the collisions between reactions. It uses classical kinetic equation methods for elementary reactions while applying the law of conservation of mass. For more detail on the process of coding itself, I have included an additional figure, Figure 2, located in the top right of my reaction section. Moving forward onto my own experiment, in order to get a good idea of what reactions were necessary to test, I referenced an article titled Helium, Oxygen, and Water Plasmas as a Source of Reactive Oxygen Species. This species observes the behavior of the ratio between water and oxygen density. I tested 5 ratios, 0.01, 0.1, 1, 10, and 100, with a set hydrogen density of 50 ppm. I wrote my own test with 35 species and 214 reactions. I have included a few of those notable reactions located in the top right of my reaction section. Additionally, in Table 1, I have provided a list of all of my species, and in Table 2, I have provided all of the list of oxygen densities for each trial. As I was examining my results, it became apparent that each reaction would run for different periods of time, despite being specified in my user code. This was caused by a lack of oxygen in the reaction. Of my list, I had far more reactions that would use O2 as a reactant rather than as a product. This caused the trial to appear to be completed as there were no more oxygen species being produced. Looking at graphs 1 and 2, this is density versus the relation of water and oxygen ratios. Graph 1 is the hydroxide species, which appears to be increasing while the ratio increases. Graph 2 shows all of my oxygen species, showing how most of them remain constant during each trial. Graphs 3 and 4 are density as a function of time. Graph 3 shows oxygen. It shows that at the beginning there is a significantly large amount per trial, but is immediately being used up to form different species, seen in previous trials. Graph 4 shows all the hydroxide species as a function of time, and it's showing a similar pattern to my graph 1. From this, I can conclude that with the reactions that I have now, the oxygen density is highly significant. It is currently all being used as an intermediate, as it is being used up faster than it is being produced. If I were to add more reactions, such as the ones listed in my conclusion section, I would see a more realistic trend. It would be useful to add more species, and it would be useful to include more reactions that would produce oxygen, as well as expanding my database to help with the reactions. In addition, I am currently working on a series of ZD Plaskin video tutorials to teach others how to become familiar with the software. I would like to thank you for taking the time to join me for my presentation, as well as thank the NSF REU program for providing me with such an exciting experience. Thank you!